Hello, we are Team 22828, and our project is 3D printing a hydrogen fuel cell. We are a multidisciplinary senior design group in the Kate Gleason College of Engineering. Our team is made up of 4 mechanical engineering majors. Tom, our team lead, Theo, our CAD lead, JP, our client liaison, and Simon, our purchasing agent. Our client for this project is Justin Pelletier, a cybersecurity professor at RIT, and our team guide is Robert Capurso, a former design engineer at Kodak. Here's a brief overview of the technology behind our project. Hydrogen fuel cells work by taking in hydrogen gas and air, which contains oxygen, to make electricity through a chemical reaction. When 2 hydrogen molecules and an oxygen molecule combine to make 2 water molecules. The cell is held together by end plates, rigid structures that compress the cell together from either end. Inside the cell, there are flow plates that have channels to allow the hydrogen and air to move to the membrane electrode assembly, or MEA, which is a thin catalyst layer in the middle of a cell that allows the reaction to happen. It is very important that the hydrogen and oxygen molecules never directly mix, as the gases could self-ignite at the standard operating temperature of hydrogen fuel cells, which is roughly 80 degrees Celsius. So what's the problem our team is trying to solve? Currently, hydrogen fuel cells are highly specialized, being expensive and difficult to manufacture. This requires a lot of specific equipment and advanced manufacturing techniques, meaning that the fuel cells must be made in a dedicated and established factory, which can lead to logistical and supply issues if the intended use is overseas or in a remote location. Our goal is to design a fuel cell that is easily manufactured without specialized equipment and with a focus on utilizing 3D printing technologies. We wanted to explore many possible options and methods to assess each idea's feasibility to be made successfully, efficiently, and with as little specialized parts and processes as possible. We initially planned to manufacture our fuel cell flow plates and end plates by 3D printing both components with polycarbonate, one of the more heat-resistant 3D printing filament types. We would then spray the flow plates with a nickel coating to allow them to conduct electricity. This idea was unable to support the amount of power we needed to put through the flow plates, as the coating was not conductive enough, and the end plates proved too weak and flexible to withstand the compression we needed to put on the cell, roughly 200 psi. We then moved to creating our flow plates as stamped metal sheets, which is commonly seen in industrial fabrication of fuel cells, and filling our end plate prints with epoxy to strengthen them. Other methods considered include using electroplating for the flow plates and metal 3D printing for both the flow plates and the end plates. Unfortunately, the price of both of these technologies led us to pursue sheet metal stamping. We faced many challenges with this project, including the repeated leaking of seals, deforming of flow plates, low electrical conductivity, and low thermal conductivity, especially when pursuing our initial idea of modified 3D printed plastic components. Stamped flow plates are harder to seal but have the potential to conduct enough electricity and heat sufficient for an active fuel cell. Our investigations of different methods in manufacturing fuel cells revealed a multitude of valuable insights. We believe that coated plastic is not feasible for flow plates, and though electroplating technology may work, it is prohibitively expensive. The end plates must be reinforced if made of plastic, as they are too flexible as standalone components. Metal 3D printing is a possible solution, however, we did not move forward with testing due to the cost and limited prototyping capabilities. Stamping is what is done in industry, and based on the limited success of our stamped flow plate prototype, it appears to be the most promising avenue. Testing the feasibility of 3D printing other fuel cell components and subassemblies, such as the hydrogen recirculator and coolant system, and much more, were not in the scope of this project. In the future, we would recommend conducting a fully metal 3D printed test. Current iteration times, budgetary constraints, and printer capabilities ruled this option out of our current analysis. As metal 3D printing becomes cheaper and the printers themselves get more accessible, this option seems very promising. We would like to thank our client, Justin Pelletier, MSD guide Bob Capurso, subject matter expert Professor Fly, and the MSD staff for all their support and contributions to our project. Thank you for listening. Have a nice day.